Hey everyone, I'm Shah. Here I'm going to talk about fine-tuning LLMs on human feedback. I'll start by explaining why we might want to do this, and then discuss two popular techniques: reinforcement learning with human feedback and direct policy optimization. Finally, at the end, I'll walk through a concrete example of fine-tuning a model to write YouTube titles based on my personal taste and preferences. The whole motivation behind fine-tuning large language models is that although base models and these foundation models are very powerful, getting them to solve problems in a practical way is not always a straightforward thing. In other words, using them isn't always so intuitive. And just to demonstrate this, we can look at a concrete example. Consider Llama 3.1. So this model has great performance across these benchmarks. It was trained on 15 trillion tokens. It has a tremendous amount of knowledge and can solve a wide variety of different tasks. However, if you wanted to use this base model for something like learning how to fine-tune a language model, and you just type in this input, tell me how to fine-tune a model, you might get a response that looks something like this. Just reading this, I am not sure about how to do this. I have a model for a small area and I have a model for a large area. I want to have a model for a large area that is as accurate as for a small area, and on and on and on. So the response isn't very helpful and is not really intuitive for people to interact with. In order to get one of these base models and foundation models to actually give us a helpful answer, we really have to do a lot of work on the prompt engineering side. So instead, I might construct this artificial blog post or something like that, where I have a title that says Intro to Fine-Tuning LLMs. Fine-tuning is where we adapt a model to a particular use case through additional training. Here are the basic steps. And then with this more structured and additional context, the model actually generates a pretty helpful response. So one, gather a data set that represents the types of data you want your model to be able to handle. Choose a base model to fine-tune. This is usually a pre-trained model that has been trained on a large data set. 3, use the data set to fine-tune the base model, so on and so forth. So really, to get base models to do what we want, we have to almost trick them into doing particular tasks, like helping us fine-tune a language model. So this was the whole motivation behind InstructGPT, which was essentially the model behind the original version of ChatGPT. So this InstructGPT paper, reference number 2, came out in 2022, and the whole thing was this process that OpenAI used to take their base model, GPT-3, and align it with human preferences. Just to see some examples of that, so if we take that same prompt that we gave Llama 3 and we pass into GPT-3, we might get a response that looks something like this. So if we say, tell me how to fine-tune a model, it'll just start listing questions, maybe kind of like a Google search or like a FAQ section on a web page or something like that. However, after this fine-tuning process to create InstructGPT, this is how the model might respond to this same input. So the response is, fine-tuning a model involves adjusting the parameters of a pre-trained model in order to make it better suited for a given task. Here are generally 3 steps for fine-tuning a model, and then it starts giving us these steps. Fundamentally, GPT-3 is doing what it was trained to do. It was trained to predict text on the internet. So it's doing a great job at that, but that isn't necessarily something that is helpful to us. On the other hand, InstructGPT was built on top of GPT-3 and is giving us a response that's more helpful. The way OpenAI pulled this off was through this 3-step training process, which at this point is quite well known, but I'll just recap it here. So the first step is the pre-training. So this is creating GPT-3 or creating Llama 3.1 405B base. Typically, you're not going to do this yourself. This is things that AI labs will do. And so you can just pick your favorite AI lab and take their pre-trained model, take their foundation model as a starting point. Step 2 is this supervised fine-tuning step. And so here, OpenAI took chat conversations, like these input-output pairs. So like a query from a human and then the ideal response from a human labeler. And so they curated this data set with thousands of input-output pairs, and they taught GPT-3 how to have a conversation like a chatbot. However, just learning how to have dialogue is still not enough, because the model still may not answer prompts in the most helpful way. Also, since this model was trained on wild internet data, there's all sorts of toxic, unhelpful, just wild things you'll find on the internet, and that stuff can make its way into the responses of the model. So there was this third step, which was this reinforcement learning from human feedback, RLHF. And so this led to a significant improvement in the model's responses as evaluated by human preferences. Not only was the model after step 3 preferred to GPT-3, but it was also preferred to this supervised fine-tuning. In the InstructGPT paper, they have a nice plot showing a comparison of these 3 models. So that's linked in the description if you want to check that out. But here I'm going to just focus on this step 3, this reinforcement learning with human feedback step. So the key difference between steps 2 and 3 from the previous slide is that step 3 uses reinforcement learning instead of supervised learning. So I actually talked about reinforcement learning in my previous video where I discussed how DeepSeek and OpenAI used it to create their recent advanced reasoning models. But the basic intuition behind reinforcement learning is that it's a way for models to learn by trial and error. So if we wanted to train an LLM on human preferences using reinforcement learning, it might look something like this, where we take a prompt, we pass it to a large language model, and we have it generate a response. And then what we do is we have a human look at the response and say whether they liked it or they didn't like it. And then through reinforcement learning, we can take this feedback and update the model parameters, pass in a new prompt, generate a response, and just do this feedback loop over and over again. So this is very much how humans learn or animals learn. So they do some behavior and they get positive reinforcement or negative reinforcement, and that'll update their future behavior. That's essentially the same idea that we're doing here with a machine learning model. However, this is not a very scalable process, because if you have to do thousands of training steps and you have a human in the loop here, and it takes a human like a few minutes to make the judgment of whether it's a good response or a bad response, this is just going to be a very slow process. So the key trick that OpenAI used in RLHF is that they replaced the human with this so-called reward model, which was trained itself on human preferences. We can think of this reward model as a proxy for human labelers, for human preferences. And so the way they created that is they took a prompt, they passed it to a large language model. So in this case, it was that checkpoint after step 2 in that 3-step training pipeline. And then they would generate multiple responses to the same prompt. Then what they would do is they would take these responses, give them to a human labeler, and these labelers had these very detailed guidelines on what was a good response and what was a bad response, and they simply just ranked them from best to worst. So the key reason why you would want to do this ranking approach as opposed to just humans saying if the response was good or bad is that if we just stop and think about it, if we were just given a response from a language model and we were told to rate it on a scale of like 1 to 10 or like 0 to 1 or something like that, like give it a precise score, that wouldn't be a trivial task to do. It would probably take us maybe 5-15 minutes to really stop and think about it. So this would just be a slow process, and even at the end of it, there's probably going to be a lot of variance. Is this response a 0.7 or is it a 0.75 or a 0.85? There's not really a true right answer. However, simply just doing relative preferences, just ranking the responses, is a much easier task. So humans can do it much faster, which allows you to have a lot more training data. And so you can take these rankings and then you can create these pairwise preference data sets. So you can basically say we have response 2 and response 3, and response 2 is preferred. So we can take 2 responses and use that to train a reward model, basically to predict which of the 2 responses was preferred. If we just take these first 2, we'll pass in like response 2 and response 3, and the reward model will learn to identify response 2 is better than response 3, and then response 3 is better than response 1. Through this training process, the reward model will learn how to quantify the quality of a given response. And so just to give you some real numbers here for InstructGPT, they used about 30,000 prompts here, and then for each prompt, they generated 4 to 9 different responses, and then they had these ranked. But the question is, how does this work mathematically? So we have this reward model that is able to generate a score score of the quality of a given response, but how can we use this number to actually update the model parameters? OpenAI used this reinforcement learning approach called Proximal policy optimization. And while there are a lot of details here, the basic thing to know is that PPO is an efficient way to update parameters based on rewards. Here's the objective function for PPO. And if you don't fully understand what's going on here, that's fine. This is for people who want to see the technical details. But if you saw the previous video where I talked about GRPO, group relative policy optimization, so that's what DeepSeek used in their reinforcement learning approach to train DeepSeek R1, you'll notice that this objective is actually very similar to what we saw there, minus a additional regularization term. That's because GRPO was actually based on PPO. But the two key features of PPO is that it uses a so-called surrogate objective, which is basically using this probability ratio times the advantage function, and then also does this clipping process. So the surrogate objective just makes training more efficient, and then the clipping makes training more stable. Since I spent like 10 minutes talking through the intuition of why this works in my previous video, I won't talk about it here, but I'll link that video for anyone who's interested. Although RLHF worked really well and led to a significant improvement in the model's performance as evaluated by human preferences, there's still a core limitation of RLHF that distinguishes it from other reinforcement learning approaches. Generally, the promise of reinforcement learning is that you're no longer bound by existing data. So in supervised learning, the model is learning by example, so it can't really get better than the available data that's out there. But reinforcement learning, since models are just exploring the space of responses on its own, it's not necessarily bounded by existing data. But RLHF is a little different because the feedback that we give to the language model is only going to be as good as this reward model. And then the reward model itself is only as good as the preference data that we give to it. This kind of brings up a fundamental limitation in RLHF, which is that there's going to be this upper bound based on the quality of the preference data. But if we kind of stop and reflect about this for a second, we might have the following question, which is, couldn't we just use this preference data directly to train the reward model? Like, why do we have to go through these extra steps of framing it as a reinforcement learning problem and all this kind of stuff? So it turns out we can do that. So about a year after the InstructGPT paper came out, this paper on direct policy optimization came out from a group at Stanford. Basically, all it does is it reformulates RLHF as a supervised learning problem. This greatly simplifies the entire training process while still obtaining the great results of RLHF. The way DPO works is that we'll get together a preference data set. Here we'll have a set of prompts, we'll have a winning response, and then we'll have a losing response. So these are just like these relative rankings. So we have two responses to the same prompt where one is preferred over the other. And then to do DPO, what we do is we take a given prompt, pass it to an LLM, and then instead of generating a response and giving feedback on that response, instead we compute the probability that our language model will generate the winning response, i.e. the preferred response, and the probability that the language model generates the dispreferred response or the losing response. With these probabilities, we can simply update the model's parameters to increase the probability of generating a preferred response and decreasing the probability of generating a dispreferred response. So fundamentally, that's all we're doing. Put more technically, this is the loss function used in DPO. So the key thing here is that at each step, we compute the probability of generating the winning response, we compute the probability of generating the losing response, and we compare that to the original version of the model. So basically the supervised fine-tuned checkpoint or whatever model you started with. And then basically all we want to happen is we want this to get bigger and this to get smaller. We want the probability of generating a winning response to go up relative to the original version of the model. And then we want the probability of the dispreferred response to go down compared to the original version of the model. So this needs to go up, this needs to go down. That'll make this a positive number. And then we have a minus sign here. So this is something we want to minimize. I won't walk through the derivation of this equation, but for those who are interested, you can check out reference number 5, which is the DPO paper. And it's just like a few lines of math where they show that you can write in a closed form the optimal optimal policy of RLHF, and then you can just minimize the difference between the predictions of whatever model you're trying to train and this optimal policy, this optimal model. Okay, so this is a bit abstract and technical. Let's make this a bit more concrete through a specific example. Here, I'm going to fine tune this model, Qwen 2.5, 0.5b, on my personal preferences when it comes to YouTube titles. And so the motivation here is that LLMs notoriously lack taste. This is why anytime someone writes a blog post or writes a LinkedIn post using AI, it's really obvious. And this is because it's really hard to kind of say why we liked one piece of writing versus another piece of writing. And it's hard to give instructions to a language model to tell it how to have my unique voice or your unique voice. These are things to kind of convey through prompt engineering, and even through supervised fine-tuning, it's hard to kind of give all the examples of what I might think is good writing versus bad writing, because this is also like context dependent and it can get quite complicated. And so the upside of using one of these preference tuning approaches is that instead of having to manually write these examples for supervised fine tuning, we can just give it these relative rankings, these winning and losing text pairs to train a model, which is much easier for us to curate and gives a better training signal to the model. To demonstrate the lack of taste of LLMs, I typed this request into ChatGPT, write me a title for a YouTube video on independent component analysis. These are some of the titles it came up with. ICA in machine learning, unmixing signals like a pro, ! Independent component analysis, the secret behind signal processing, the magic of ICA, separating mixed signals with AI, blind source separation with ICA, unmixing audio, images, and data. Just reading these titles, like these are all bad. And I don't fully know why they're bad, but some things that come to mind is like, I don't like this unmixing signals like a pro. That's like very vague. It sounds like it's trying too hard. It's trying to be engaging and sticky, but it's just not. It just sounds AI generated. Another one is the secret behind signal processing. So this is kind of like a similar thing. You're trying to make it a little clickbaity, but does that really make sense for a educational video on independent component analysis? I do like this format though. So you have like the keyword, the thing that people are actually searching if they're curious about this technique, independent component analysis, but like this here is just unnecessary. This doesn't really do anything. And again, like people might have different preferences and different opinions, and maybe you love this title for whatever reason, but me personally, I don't like it. The magic of ICA, like that gives me no value. Separating mixed signals with AI. I feel like this last one is probably the best because it's like the most accurate. It's the most informational, but it's just a bit too long. If it was just independent component analysis, unmixing audio, images, and data, like maybe that wouldn't be too bad, but still kind of long. Let's see how we can use DPO to fine tune this model on my preferences. Here's an overview of the process. The first step is to curate the preference data. Next, we'll fine tune the model using direct policy optimization. And then finally, we'll evaluate the fine-tuned model. And then I'll just call out that all the code that I used for this example are freely available on GitHub, linked here and in the description. Additionally, the preference dataset that I use, as well as the fine-tuned model, are freely available on Hugging Face. I think I made this all Apache 2.0 license, so you can freely use any of this code or data or this model however you like. Okay, so the first step is curating the preference data. So this is the most important and most time-consuming part of the process. This is essentially the whole project, curating the preference data, because this is essentially how we're programming the computer, how we're telling the model what's a good title, what's a bad title. My process for doing this is I wrote out manually 114 different video ideas, and then for each idea, I generated 5 title ideas using Qwen 2.57b instruct, and this was via Together AI's API. And I just used the API because it's much faster than running all this on my laptop. And then for each idea, I created 10 different title pairs. If we have 5 titles for each idea, we can do 5 choose 2, and that comes out to 10 unique pairs. And then the fun part of manually reviewing all 1,140 title pairs and labeling which one is better, which one I personally prefer. And so 3 hours later, I have a data set that looks like this. So I have the idea, I have title A, title B, and then I have this column which indicates which one is preferred. So 1 means that title B is preferred and 0 means title A is preferred. Reading these, like top 3 text embedding models every data scientist should know. I feel like that's quite sticky, but that doesn't make sense. There aren't 3 embedding models that every data scientist should know. I just don't don't think you can really fulfill on that promise in a video. However, title B, text embedding models from theory to practice, that makes sense. That seems like a video that I would actually make and probably actually watch. So I prefer title B. The next one, master multimodal RAG in just 10 minutes. Okay, that's pretty good. And then why multimodal RAG is the next big thing in AI. This next big thing in AI is just kind of like vague, and I'm not sure like what that means or even if it's true. I can't think of a narrative around that, so I went with title A in this case, and then so on and so forth. This is definitely very time consuming. I thought it would originally take me 30 minutes, but it turns out it took me longer because some pairs are obvious, but other pairs are not obvious. And then there are some pairs where they're both bad. So like this one, the beauty of fractals exploring infinite crinkliness, and then the math behind fractals, crinkliness, and beyond. I wouldn't use either of these, but I still just picked which one of the two was less bad in these cases. And so I won't share the code here, but it's on GitHub to do this whole process, to take the video ideas and generate the synthetic titles from them. And then of course the labeling was done just manually, and I used Apple numbers to do that. But then once I have this preference data set, I reformatted it like this. So we have this triplet of prompt, chosen, and rejected. So this is like prompt, winner, loser that we saw before. And then I formatted everything as a list of dictionaries because that is the expected format of the TRL library from Hugging Face, which is what I used for the fine tuning. This data set is again available on the Hugging Face hub. It's called YouTube Titles DPO. And then the notebook I used to translate the preference data set into this format is also on GitHub. Now that we have our preference data, we can use it to fine tune the model. First thing we'll do is just do some imports. This is data sets from Hugging Face. So I'm using the TRL library to do the training. TRL has a lot of different reinforcement learning approaches. So they have implementation of PPO, which was used in RLHF. They have an implementation of GRPO, which was used for DeepSeek R1. So there are a wide range of reinforcement learning approaches available in this library, but I just kept it as DPO to keep it simple. Then I import the transformers library. So this has some handy things for importing the model that we're going to fine tune, its tokenizer, and generating responses from it. And then I also import PyTorch. Then I load in the dataset and the model. So the dataset is what we saw in the previous slide. The base model is this one. So I'm using this instruction tuned version of Qwen 2.5. The model that you fine tune here doesn't need to be a base model, and it probably shouldn't be a base model. In fact, it would probably be good to take this instruct model, train it on title examples through supervised fine tuning, and then do the preference tuning. But I skipped that step for this project. Then I'm importing the model, importing its tokenizer, and then I just added a pad token here. Next, we can just get a sense of how this base model performs this title generation task. So I set up this pipeline, this text generation pipeline, pass in the model, the tokenizer, and then I pass in a prompt. The data set actually has a train validation split. I just grabbed the first example from this validation data set, and then I have this custom helper function, which just puts it into the correct format. I'm not going to show it here because it's just kind of long and not really central to what we're talking about, but if you're curious, it's on GitHub. So that creates this prompt, and then I just pass the prompt into the text generation pipeline, and it'll generate an output. And so this is what Qwen 2.5 0.5b comes up with. The video idea was independent component analysis intro or something like that. And so the title it came up with was Unlocking Independent Component Analysis, the Key to Understanding Your Data. So again, this kind of has like that hacky voice, that hacky vibe that we saw from the ChatGPT ideas. For whatever reason, it loves to put some word like unlocking or revealing or something like that at the beginning of the title for whatever reason. And then it likes to have this vague, pseudo-engaging part of the title as well with some exclamation mark. So let's see how these responses improve through fine-tuning. First, I'll define some training arguments. Here, I'm just creating a name for the fine-tuned model. So all I'm doing is taking the original model name and replacing instruct with the DPO. So that'll call the model Qwen 2.5 05b-DPO. And then I have various training arguments here. So key ones here are I use a batch size of 8. I train for 3 epochs. I load the best model at the end. And then the metric used to evaluate what model is best is the evaluation loss. So this will be the loss from the validation data set. And then I'll save a checkpoint of the model at every epoch, and then I'll print evaluation metrics every epoch. And then with that, that, we can just simply train the model using this DPO trainer. So I pass in the model, the training arguments, the tokenizer, and then I have my train validation split for the train and eval data sets. And so here's what training looks like. So just trained it for 3 epochs, took about 8 minutes on my MacBook. But we can see that the training loss is going down, which is good. But then we see the validation loss starts going up on epoch 3. So a little bit of overfitting. But we have a whole lot of other metrics we can use to evaluate the performance. I guess the key ones here are like reward margins. So this is basically like the difference in rewards between the preferred and dispreferred responses. And then reward accuracies is basically the percentage of times that the correct response is preferred. And then these two are just the average reward to the preferred responses and then the average reward for the dispreferred responses. All these give us a slightly different perspective on how the model is performing. So even though the reward margin keeps increasing, which is a good thing, we have the accuracy increasing and then dipping again, which kind of tracks with the validation loss. At the end of it, we'll load the checkpoint from epoch 2 and then we'll pass it through the same exact code to generate a title. And now we have this title, Independent Component Analysis for Beginners. And so this is much more aligned with something that I would actually write. Maybe I would add like with example code or with Python code in like parentheses after this, but this is much more aligned than the previous title. While just kind of looking at one title gives us a nice vibe check of how the model is performing, this is not a very robust evaluation strategy. So here, let's do a proper evaluation of this fine-tuned model. One of the key downsides here is that we're trying to evaluate how the model performs based on my personal preferences. So there's really not a great way to automate this. There's not a metric we can take off the shelf. And this wasn't something I could get working with an LLM judge. So I tried several attempts to get GPT-4o to align with my personal preferences, but I couldn't get it to consistently agree with my preferences. Ultimately, I just went and manually evaluated the responses. So the process looked like this. I picked out 50 random video title ideas from that initial list of 114. For each of the ideas, I generated a title using the base model and the fine-tuned model. And then I created these 50 pairs. So I created this face and fine-tuned model pair, and then I assigned a preference label to each of them. And then I computed how often the fine-tuned model titles were preferred. And so this is what that evaluation data set looks like. So we have the base title, the fine-tuned title, and then a flag that says the fine-tuned title was preferred. And so just reading the first couple ones, this one from the base model wrote, from physics to data scientist, my journey through mathematics. I didn't study math, but let's see. The fine-tuned model said, how I became a data scientist, my journey from physics to science analytics. So science analytics isn't really a thing, but if you just drop the last few words, like this is a good title. How I became a data scientist, my journey from physics. Like I feel like I would use that. Exploring topology secrets and data analysis, topological data analysis techniques. This topology secrets is not doing it for me. Let's see this one. Exploring topological data analysis, a comprehensive understanding. Okay, this isn't great, but I feel like this is closer to something that I would actually write than this one. A comprehensive understanding, that's not good. Maybe a comprehensive guide or something like that. So I preferred the fine-tuned ones in these first several rows, but let's look at this one. Understanding entropy in everyday life, a simple explainer. It's not great, but there could be something there. But then this one is quite wonky. So entropy of a system, the measure of disorder in a system, the less disorder there is, the. So it seemed like it wasn't even trying to write a title. It was like trying to write like a paragraph or something. So the base title was preferred here. And then mechanistic interpretability, unlocking the secrets of AI's hidden algorithms, or mechanistic interpretability in video, exploring the limits of machine learning models. I feel like these are both good, but like this mechanistic interpretability in video, like that doesn't make sense. So one thing that was happening is Qwen was getting confused because the prompt said, write me a YouTube title idea based on this. And for whatever reason, it wanted to put video or YouTube video in the title itself, which is just not necessary. So I did this for like 50 different pairs, and then the fine-tuned titles were preferred 68% of the time. And then if you're curious about how I created this data set, that's available in this notebook here, available on the GitHub. That brings us to the end. If you have any questions or suggestions for future content, please let me know in the comments below. And then if you want to dive deeper into any of these topics, check out the references and the resources linked in the description below. And as always, thank you so much for your time, and thanks for watching.